we'll start out today, we'll talk about 2D crystal systems and lattices. But just before that, a little bit more on point symmetries. So, under point symmetries, you have seen several of them, and one was reflection, another was rotation, etc. But right now, since we're going to talk about 2 dimensions, these are the 2 important point symmetries that are present in the 2-dimensional situation. Now, why do we call them as point symmetries, and how are these point symmetries different from translation symmetry? So, let me first in a way define what is a point symmetry. So, after a point symmetry operation, there is at least one invariant point. Now, let us see what does this definition mean. So, let us just take a couple of examples through which I will explain what is the meaning of invariant point. So, let us say that I have a mirror, and on this mirror I put an object on one side. This is a what I will call it as an asymmetric object, since it has no symmetry, or we can say it has one-fold rotational symmetry. Now, this mirror will reflect the object onto the other side like this. So, if I call the first one, let us say, as a right-handed object, then this, after reflection, this has become left-handed. Now, if we notice, all the points in space have moved after a mirror operation, except for the points which are on the mirror itself. So, I can write here that in the mirror line, no point moves, and such points are what are called as invariant points. So, for a point symmetry, at least there should be one invariant point. Now, consider the case of rotation. Let us say I have a three-fold rotational symmetry. So, this symbol of triangle basically indicates that it is threefold. Now, let us consider an object at some distance, an asymmetric object at some distance. Now, since it is a threefold, we can rotate this axis by 120 degrees, and this object moves to another location. So, this object is copied there. So, this is 120 degrees. Another 120 degree rotation, and the asymmetric object will come at this position. In this rotation, there is no change in the handedness of the object, and these angles are also 120 degrees, and another 120 degrees will come back to from where we started from. Now, here, where are the invariant points? So, the invariant points in this case are on the rotation axis. Now, how does this differ from translation symmetry? Well, in the case of translation, every point moves in space, and therefore there are no invariant points. Though this definition of invariant points may look trivial, but it comes in handy when we are trying to solve some symmetry related problems. Now, let us look at 2D lattices in some detail. So, 2D lattices, what we want to look at, what are the various crystal systems I can have, and what are the conventional what tools we use to get the crystal systems and the conventional unit cells. The same methodology then can be used to evolve the three-dimensional Breve lattices. So, how do we do this then? So, what we do, we add point symmetries to a translation vector. So, let us say my translation vector is A, and the various point symmetries that I have are one-fold, two-fold, three-fold, four-fold and six-fold, and in addition I also have a mirror. So, one by one we will try to add these point symmetries to this vector A and see what is the result of operating the point symmetry on the vector itself. But what I will do is, I will first take up four-fold rotational symmetries. This is something we have seen in an earlier lecture, we have seen the square crystal system and the primitive square unit cell, in which there was four-fold and there were several other symmetries as well. So, let us just take a look at that situation first. So, let us say that I have, this is my vector A, add to this vector the four-fold point symmetry, and let this point symmetry operate on this vector. When I do this, this vector will rotate through 90 degrees. That is one of the symmetry operations for the four-fold. So, I will get another vector as a result of this operation, and let me call this vector as B, and clearly this angle alpha, which is 90 degrees. So, now based on this I can even get a unit cell, and I can put the lattice points at the corners and get a primitive unit cell. Now, since there is a four-fold, actually this unit cell naturally comes out to be a square, and hence the crystal system that we call this is, we can call this as a square crystal system, and the unit cell to define the lattice, which would be putting the corners on this particular cell. So, I can put the lattice points at the corners to obtain a primitive square unit cell. And of course, we can see that in this case A equals B and alpha equals 90 degrees. But let's just take a different unit cell to define the same square lattice. So let me draw another adjacent square unit cell again. In this case, I will have lattice points again at the corners, and the new cell that I will get would be something like this. Now, in this case, if I try to see what are my lattice parameters, so I can say that this is A prime bar, while this vector, let me call it as B prime bar, but B prime bar is also equal to the red cell vector B. Now, if I were to put the relations, and at the same time this angle is going to be alpha. So, one can sort of very quickly write that A prime not equal to B prime and alpha not equal to 90 degrees. But analyze this a bit. If you look at the A prime vector is a diagonal in the square unit cell, and since A is equal to B, I can write, and B prime is equal to B, I can write this as A prime upon B prime, that is the ratio of the magnitudes of these two unit cell vectors, would be equal to square root of 2. Now, I can directly write, it's very straightforward, that alpha equals 135 degrees. This is essentially 90 plus 45. So, even here there are constraints put on the lattice parameters or the unit cell parameters, and these are very specific constraints. And in the primitive square cell, these are the constraints. And these constraints are as a result of the fourfold rotational symmetry. And hence, we should not directly judge that what crystal system something should belong to depending on whether the parameters are equal or not, or whether they are equal to 90 degrees or not. That is an incorrect, as I had indicated earlier as well. So, this makes it clear. So, this is my first unit cell that I have developed based on a fourfold rotational symmetry. It's a square crystal system and the primitive square unit cell. Now, let us add other symmetry elements. Let us add one-fold. One-fold means no symmetry. And let us again start out with a vector A, and since there is no symmetry, how do I choose the second vector B? So, since there is no symmetry, there are no restrictions imposed on the vector B, and hence I can choose a vector like this arbitrarily. And if I now look at the shape of the unit cell, it is like a parallelogram, and the vector A and B, the angle they make with each other is alpha. So it can be called as a parallelogram crystal system, or I can refer this to as oblique crystal system. And once I put lattice points at these corners, I will get primitive oblique lattice. I should write no constraints on A, B and the angle alpha. So, here at this stage I want to put it why I am writing it like this and as not as A not equal to B is there can be a coincidence and the two parameters may be equal, A equal to B. There can be a coincidence when alpha may be 90 degrees, or if you make some measurements using X-ray diffraction of these parameters, within the experimental error, the diffraction data may show that A is equal to B, but that does not mean that it will become a particular crystal system just because from that experimental data you found that it is A equal to B. Or another way to say that what does not equal to sign mean, one can put not necessarily equal as is introduced in a few in some literature and books. But let us keep it like this, no constraints on A, B and alpha, and when you see A equals to B, that means there are constraints. If you see alpha is equal to 90 degrees, then there are some constraints, because when you choose a different unit cell, then the constraints will change. Now, let us take another point symmetry, two-fold rotational symmetry. Now, we again do the same exercise. Take the vector A and I add two-fold, which is the shape of a lens. Now, what will the two-fold do? It will do a rotation by 180 degrees. So, let us rotate this vector. So, I get 180 degree rotation. But this does not define the vector B, because all I have done by this rotation that the vector A has been flipped in the opposite direction. So, in a lattice translation vector, the vectors work in both directions to generate the lattice. So, therefore, this is simply the vector minus A. So, what does this mean? Well, this means that again the second vector B has no constraints with vector A. So, I again get this unit cell and there is an angle alpha with between the vectors A and B, and then again A not necessarily equal to B, alpha need not be, alpha can be any angle, which means that all I have done by adding a two-fold rotational symmetry, I have just created again, if I put the lattice points as well. So, it is again primitive oblique, say that is same as one-fold. So, an oblique crystal can have a one-fold symmetry or a two-fold symmetry. So, we can say that the minimum requirement is a one-fold. Two-fold may or may not be there. I have done one-fold, I have done two-fold, I have done four-fold. Now, we are left with three-fold, six-fold and mirror. So, let us start with three-fold. I add a three-fold rotational symmetry. Now, this as you know will rotate this vector by 120 degrees and I will get another vector B. Now, one can see in this case that the magnitude of the two vectors would be same the way I have drawn it, and again I can put the lattice points at the corners and I get a unit cell where A is equal to B and alpha is equal to 120 degrees as a one specific case. But before I name this crystal system and the lattice, I also want to look at what happens when I add six-fold. So, now when I add six-fold, same exercise, Now 6-fold means I can give a minimum rotation of 60 degrees. But remember, I can also rotate by 120 degrees. That would also be fine. But let us rotate by 60 degrees. So if I want to see one possible unit cell that I get is a kind of a rhombus with 60-degree angle here and 120-degree angle here. Now if I compare the unit cell, one of the unit cells that we derived when we added 3-fold and then we look at 6-fold, are these two unit cells different? Actually they are not, because even in this cell, if you look at the 3-fold cell, the cell that generated by the 3-fold rotational symmetry, this is the 60-degree angle. So both the cells, it's just a question of orientation. And therefore, both the unit cells actually define a very similar lattice, same lattice in fact, the symmetries could be 3-fold or 6-fold. So both of them are clubbed into one particular crystal system, and we will just call this as the hexagonal. It is also sometimes called as trigonal, but we will prefer the name hexagonal. So hexagonal crystal system, and once you put the lattice points and decide on a unit cell, then A equals B and alpha equals 120 degrees. So now these are how many crystal systems we have developed? We have developed square crystal system, oblique crystal system, and the hexagonal crystal system. So I have got so far 3 crystal systems, and but we still, so I should write this as so far, but we still have to we still have one point symmetry left, and that is the mirror symmetry. So we will see what happens when we add a mirror to a translation vector in the next lecture.